Hello, dear prospective candidates for the PhD program in Department of the Mechanical Engineering. I'm D.K. Dwivedi, Professor in Department of Mechanical Engineering. You see, I'm recording this message because I'm out of town today for some urgent work, and therefore I hope that what this small presentation will help you to get the idea about the kind of area in which I'm looking for a PhD candidate. So these are the few potential topics. I will elaborate these topics later. The diffusion brazing of the steel and aluminum alloys. Currently, we are working on the induction brazing of steel and aluminum alloys. We have planned to work on the diffusion brazing of these two systems. Then another one is the functionally graded dissimilar steel weld joints. Due to the difference in thermophysical properties, when the two different steels are joined together, they create a lot of issues related to the residual stresses, cracking, and metallurgical incompatibilities. So it is proposed to develop the functionally graded dissimilar steel weld joints. Like nowadays, people are talking about the green hydrogen and its commercial use. For that, we need certainly the hydrogen storage tanks, which are usually made of the low carbon steel. So the hydrogen embrittlement is a common problem in these steels. In the hydrogen storage tank steels, and it's controlled using the multi-material cladding. So this is one of the proposal, like developing the functionally graded materials cladding over the surface of the low carbon steel, so that the access of the hydrogen to the low carbon steel can be minimized. Another new topic on which we are working currently is the dissimilar metal joining, magnetic pulse welding. Actually, this is the electromagnetic based welding process where the joint is developed in the solid state. When we go for the dissimilar metal joining, it would be the best, like say A and B, two systems need to be joined. So it will be the best if the two can be joined without doing anything. That is the best possible solution, but it is not possible actually. Nothing happens automatically on its own. Okay. So this automatic joining of A and B is not really possible. We need to apply either force or heat for that purpose. So we can apply like the brazing or soldering kind of thing between the two. So this will be leading to the very minimum effect on the base metals which are being joined. There may not be any melting also. But when we use the lot of heat for developing the for melting the edges of the components A and B to be joined, then it leads to the development of the weld joint, a weld metal which may be very hard, very brittle due to the metallurgical incompatibilities, and it also develops the residual stress, a heat affected zone both the sides, apart from the development of the residual stresses due to the differential thermal expansion behavior. If we can develop a weld joint with the minimum possible heat, then it will be the best. But actually this is not workable. Why? Because when we use the heat for the fusion, development of the fusion weld joints, then we need to apply an optimum amount of heat, because either higher or lower amount of heat will degrade the performance of the weld joint. So if we see, the optimum heat will result the best joint characteristics. So this is the optimum amount of the heat. If we go with the lower heat input, then it will result in the increased weld discontinuities and the stress ratio, which will degrade the joint performance. So this is like increasing issues due to the reduced heat input. On the other hand, if we use too high heat input, whether we are developing the same similar metal joint or dissimilar metal joints, in that case, so use of the too high heat input will degrade the microstructure, mechanical properties, and even increase the residual stresses. That's why it is important to use the optimum amount of the heat. So as I said, in the dissimilar metal joining, if you see, these are the important aspects that govern the ability to develop a sound weld joint and the joint performance. One is that differential chemical composition leads to the problems like the formation of the unfavorable metallurgical things in the fusion zone. Okay, there may be unmixed zone formation, there may be unfavorable intermetallic formation. Then differential melting point can also create a problem, like the melting point of the steel is, say, in one hand it is 1500, on the other hand it is, say, just 600 700 degrees centigrade. Then thermal conductivity, lot of difference in thermal conductivity also leads to the varying distribution. The heat rate of heat dissipation will be completely different in the two cases, and thermal differential thermal expansion coefficient leads to the differential residual stresses being developed on the two sides. So differential thermal conductivity, differential melting point, and differential compositions lead to the asymmetrical weld joint like this. If you see, heat is being applied at the center, but the weld is skewed towards the one side, it is shifted towards the one side. So this leads to the differential penetration, and the formation of the unfavorable metallurgical constituents in the weld zone leads to the, that's why it is important to understand and investigate the various possibilities related with this. If we see, if just for an example, if we see the austenitic stainless steel is welded with the ferritic steel, then direct conventional welding, direct connection between the two metals without any use of filler, it leads to the lot of a difference in the composition across the two components. Like this side ferritic steel is, this side austenitic stainless steel, then there is a sharp gradient, sharp change in the composition in terms of the nickel and chromium equivalents. So if you see, the black one shows the variation in the nickel equivalent, and the green one shows the chromium equivalent, and such large difference leads to the lot of variation in terms of the mechanical properties, thermal expansion and contraction behavior, which in turn develops the residual stresses and increased cracking tendency. So if we go for the functionally graded weld joints, then we can use the different layers of the functionally graded materials, having FG1W, FGW1, FGW2, and FGW. You say these are the three different kind of the materials which are being applied for developing the weld joint across the ferritic and austenitic stainless steel joint. In this case, like say, the gradient for chromium and nickel equivalent will be reduced. Okay, and this reduced gradient will actually be helping to minimize the issues related with the dissimilar steel joining or magnetic pulse welding process, where the electromagnetic force is used to ensure the high speed and high force impact between the two components to be joined. This in turn leads to the micro level of the interfacial deformation at the interface, and in order to minimize the harmful effect, sometimes we add the filler at the interface. The red one is indicating kind of filler, and this side the two are indicating like if they are forming some kind of the IMC on both the sides due to the interactions between the two. The ultrasonic welding and the magnetic pulse welding are the and explosive welding are the example of this kind of the joining process. We have planned to actually develop the magnetic pulse welding system. The diffusion brazing is another area in which we have planned to work in, where like say the metal A and metal B is being joined, and conventionally what we do, we try to select the material which is compatible with both as a brazing material and offers the reasonably good the joint strength. So in conventional brazing like the furnace brazing or induction brazing, a thick layer is left in between while forming some kind of the IMCs at both the ends, which primarily determine the joint strength if they are hard and brittle. Otherwise, the brazing material itself determines the joint strength. That's what we can see here. If we see the magnified view of this, then we will see the variety of the IMCs are being formed. It's important that these IMCs are really favorable for good joint strength, as compared to this conventional one when we use the diffusion brazing. So in the beginning, definitely we have to apply the brazing material, but during the course of the diffusion brazing process, this entire brazing material gets diffused out. This leads to the joint strength which is almost as good as the strength of the one of the base metal, which is weaker. Okay, this in turn leads to the fourth one is where low carbon steel tanks, okay, which will be cladded with the functionally graded material, say, which is shown in form of the different layers. So this system will be charged with the hydrogen, and we'll see that as a function of time how the embrittlement of the low carbon steel is getting affected. But just for the simplification of the process, this is actually our net goal. So our simplification of the process is like we'll take a simple very low carbon steel, and then we'll be doing the cladding of the variety of the material, just like this multi-material system, and then this will be charged with the hydrogen, and to see the extent of how it is getting affected when there is a cladding, when there is no cladding. So this is another kind of the problem in which we plan to work in. Now these claddings can be developed using the additive manufacturing approaches like the wire arc additive manufacturing or the similar kind of the processes.